All right, so this is all about the LML signature and all the discussion that, well, my screen, just a second. Yeah, all the discussion that we wanted to have around here. Maybe this should be fine. And so, the proof is more or less the same. We don't have to go through the proof. Just for your knowledge that we also have, we can design a signature scheme using discrete logarithm problem. So I think just now we've discussed the RSA that works on the regular ZN groups, and the security relies on factorization problem. Now we've seen that we can design encryption and digital signature schemes based on discrete logarithm hard assumption. So these are two things that we've discussed, and now we see an example of different crypto systems or digital signature based on different hard assumptions. But instead of going to the security proof, I would like to take you to some security analysis. This would be very interesting things to learn. So we go through them one by one. So if you see the design of this scheme, so it look like that if you know the key, if you know K, let me go back over here. So you know that we start with, drawing a random K, and then compute R, which is G to the K, and S from this formula. So it turns out that when you sign some message and then you leak this K, what happens is that you can recover the secret key. That is very dangerous. But looking into this equation that is a part of the signature, so you will share S to everyone. A message you also share that what message you sign. S is a part of the signature, so of course you will share. And then when you leak K, then everybody can also compute the inverse of K. And then R, if you go back, is nothing but G to the K again. So the value of R is already part of the signature, so everybody knows about it. So it turns out that when you leak K, people can compute inverse of K. And if you look into this equation, you have one equation, one unknown, which is X. So then we can solve this problem to retrieve the signer's secret key. So there should be no way when you generate the signature, you should be very careful that you cannot leak this randomness key that you generate in the first step, and that could be very dangerous if you ever do so. So be careful about this one. So it is a very good thing to note that we shouldn't leak or randomness that we generate. And also the second one is there is attack for when we use the same same randomness for signing two messages. So here I have an example. I use the same K that I generate, and you see that the first part would be the same, and only the S would be different because message which are different, two messages, M and M prime. I use that same K to sign both of them. So for the first one, we have R equals to G to the K, and then S is K minus 1 M, and then RX. So all of these are fixed except M. And then for the second one, again, when we fix K, so the first part would be the same. For the S, we get S prime, not just because we do many different computations, just because M prime is different than M. And therefore, we get this. The only difference that we get is the S part. We get S and S prime correspondingly. So now it turns out that we can, if we minus these two parts, so we say S minus S prime, so what we get is M minus M prime inverse of K mod P minus 1. So the truth over here is that we can compute this K now. How so? Because we know the S, it is a part of the signature. We know S prime, it is a part of the second signature. M and M prime, we know them because, when we reveal M when we do the signature. And P minus 1, of course, we know. So we have one equation again and one unknown, which is K, and then we can definitely compute this K. And then when we compute the K, it becomes even more dangerous because we can go back to the previous step. We know the K, now we plug into this formula, just one of them, and then we can recover the secret key. So we need to be very careful. 1, to choose the random key, do not share it. 2, do not use the same key, K, to sign different messages. For every message, we are supposed to use a different randomness. And if we don't do so, we don't just leak our K, we can also leak our private keys, and that is going to be very dangerous. We need to be very careful about that. So there is another one that this scheme with what we call it the textbook design, it turns out to be existential forgery. And so we know that it is very hard to compute given this MRS from, it is very hard to compute it from this value directly, but it looked like that there is a way that you can forge a signature of some random message without even knowing the private key. So somebody can just utilize the public key and sign some random messages on the behalf of the person that owns the private key. And that's what we call it existential forgery. And this is not a good thing to have at all. So it turns out that the way that we can do so, we can choose some value B and C, but to make sure that the GCD of C and P minus 1 is 1, because then C has inverse. And then it means that this means that C has the inverse. So C times C minus 1, if we call the inverse, should become 1 mod P minus 1. So there is an inverse for C. And then we can compute C minus 1 based on extended Euclidean algorithm. So far we didn't do anything. So it looked like that if we take these steps, we can, forge a signature for some random message. It's not a message of our choice, but it could be any message, random message. But the word existential forgery, it means that it is possible to sign some random messages. Ideally, we want a signature scheme that it is not possible to even provide a valid signature of some random or meaningless message. But let's see how we can forge a message now. So it turns out that when you want to forge a message, you can choose a B, you can choose a C with this condition. And then a forgery of the message is this one. So I will walk you through this one. So it look like that your message is some minus R, B, C minus 1 mod P minus 1, and then R set to be G to the B, Y to the C, and S is going to be this one. And if you pass this 3 tuples to the verifier would say, yes, this is a valid signature. But we know that we didn't have the private key, but it looked like that they can just use the relationship in the verification algorithm to come up with this forgery. So let's see how it works, because we know from the verification algorithm that we know that Y to the R and then R to the S should equal to G to the M. Okay, this is how the verification works. So let's see if that is the case. If this is a forgery, and let's see how the verification algorithm would say yes for this one. So let's continue. So take the first part. We said Y to the R, R to the S equals to what? So we keep y to the r, and then we go for r. According to this new forgery, this is going to be r, this is our m, and this is our s. So our r is, they define it to be g to the b, and then y to the c, and then to the power s. So let's continue with this. We get y to the r, and then g to the b, and then y to the c, and then s. They already have a defined value, which is minus r inverse of c. Right? So if we continue from here, we know that y equals to g to the x. So to the power r, we get g to the rx, right? And then multiply 2. So let's get this together. We get g to the power minus b rc inverse. And then from the second part, we get g y is already g to the x, so we get g to the minus x c inverse r, right? So that would be the entire thing that we would get here. Remember that y equals to g to the x, so g to the x to the c is g to the xc, and then when we multiply this one, so we get this all over here. So we know that c and c minus 1, they will cancel each other. They are inverse of each other. So from here, we get g to the rx times g to the power minus b rc inverse. And then from here, what we get left is minus xr. So you see that this g to the rx and g to the minus xr or rx, again, they will cancel out each other. So the whole thing would equals to g to the minus b r c minus 1 inverse of c. And you see that we start from here and we derive this one. So this means that from the choice that we made for r and the choice that we made for s, for this verification algorithm to be correct, then m has to be minus br inverse of c, and that's what they set m to be, this value. And so when you get this value, you raise it to the power m, then you see that these two values are equal, and therefore the verification algorithm would say that yes, this verification would hold true. And that is exactly what the attacker was hoping that it happened. So this is obviously not a good thing to happen at all. We really want to have a digital signature scheme that it is not even possible for somebody to forge a random message, to forge a signature of a random message. In practice, a lot of people would say, well, I normally want to, sign some meaningful messages. Like, let's say my message is a Word file, it's a text file, it's some, English text. What they are providing me here is the message is some random value that it is very unlikely that this thing turn out to be some encoding of, English text. That's true, but the point is a lot of time we also use the signature for some numbers, and when you want to sign a number, then you have a different encoding. Then it is hard to tell whether signing some integer is valid or not, because at the end of the day, you should be able to sign any integer. So it turns out that sometimes it would become challenging depending on your application. So one of the ways that we can fix this in practice is to sign a message, to hash a message instead of just working with the message directly. So suppose that we have compute the hash of message before we go here. So we compute something and then we get that the hash of the message, the value of the hash, so hash of message equals to minus BRC minus 1 if we were to use hash function. Then we know that computing the inverse of the hash is another hard problem. So then we don't know m, right? Because the hash, we know that the computing the inverse of hash, because if we are using cryptographic strong collision resistant hash functions, then we know that given the hash value, computing the inverse of hash value should be very hard. So even though somebody can perform this attack, and according to this description, this value should be the output of the hash of the message. And so when you want to send your signature, you need to send your message, not the hash of the message. We only do hash of the message within our computation. So then, even though you find a forgery using, by setting the hash of the message to be some value, but you don't know what is that corresponding m to this hash function is, because the hash functions are difficult to find the inverse, and therefore, the properties that we have in cryptographic hash function comes handy here, and it would help us to make sure that the scheme that we've created turn out to be secure. And this is fantastic. You see, like some properties that we discussed in a hash function, some people may think that, oh, those are not very necessary. Why do we have to have that? Those would make the design of the hash function more difficult and so on and so forth. But now you see that when you have those properties for the hash function, then you can utilize them somewhere right like here, that you can turn some scheme that is existential forgery, existential possible to forge some messages. You just turn them existential unforgeable. We just plug in a hash function and that's it. We didn't do much. We just compute the hash of m throughout the computation instead of working with the m directly. And of course, we said that this would also bring us another benefit using hash function, because when you generate the key, we said that in the beginning that the message that you can sign over here, that the length has to be less than p minus 2. And what if like you generate your key, and then right now you think that you would basically sign a small messages, but all of a sudden you start to have this request to sign larger messages, and then it would be sometimes not easy to go back and change your keys, because everybody got your key, and somehow in some situation it would be a hassle. So the best practice is to just get find a good prime p that is large enough, and then you would basically, instead of plugging m directly, you would plug in the hash of the m. You know that no matter how large your message is, the hash of your message is always compact and small, and that means that no matter how small or large the length of your message is, as long as the hash of the number of the bits on the output of the hash function could be supported in your group, then you're good to go. You can basically sign any message that you wish. Right. So I hope that I brought up, instead of the security proof, I brought this topics over here. I think these are way more important for you to learn, especially for this applied crypto course. That small mistakes, like somebody would reveal this randomness k, somebody would use the same key to k to message two different messages, or someone that doesn't want to use the hash function, then you see that how insecure your digital signature can turn into. At least lessons are learned, and then when you want to use them in practice, you won't make this mistakes anymore. So right, so one last thing that I wanted to just kind of feed in, just even the description, I think it would worth it to discuss the DSA signature. So the DSA is known as digital signature algorithm, and the truth is, if you check your browser for most of the website that you connect to, then you see that the default or preferred signature scheme is the DSA, even though you use RSA for encryption. For the digital signature, DSA is very popular because it is a standard. And I thought that it would be interesting to just have some small talk about it. You don't have to go through the details, but just like knowing how does it work, it would be a good help to understand the requirement in the future if you're working in the field. So let's start with the key generation, typical just like every other algorithm. So we are expected to find a large prime P that has this format, so as K, Q plus 1, and then we also need to find the generator of G under the GQ, not the GP. So let's see, let's have some thoughts over here. How do we do those things? So the first one first is that we need to find a random prime Q. So we start with finding prime Q such that the length of Q is 160 bits, right? That was the requirement, or any other length, right? So so we find this Q, and then we look for a prime P in this sequence of numbers. So we start with 2K Q plus 1. We do 2K plus 1, Q plus 1, and then so forth, right? So we check, and this is not a prime. We continued, and we get the same number, not a prime. After some point, 2K plus I, Q plus 1, then this is turn out to be is a prime, right? So once we found that this number is prime, then we know that we found or P. So or P is basically, we would treat all of this as K prime Q plus 1, okay? And there we go, we have our P now, which is a prime. So that means that we can form more group Z star P, which is all the numbers from 1, 2, 3, all the way to P minus 1, right? Because P is prime, so everything is co-prime, so they are all in the set. Interesting. So we found or P. So now the second task is a little bit different, is that we said that we want to find a generator G of this subgroup GQ. So we know that by our design, this group can have two subgroups. It could have a subgroup of length 2. It could have a subgroup of length K plus I, and then it could also have a subgroup of length Q. We need to test those things. We suppose we test. The only thing that we have to make sure is that the subgroup of length Q exists, and that is the group ZQ that we are going to work on. So since we are going to work in a subgroup of this, we need to find a generator of that subgroup, not the generator of P. So we know that from a generator perspective, from Euler, we know that if some value is a generator, some G is a generator of ZQ, then the order of ZQ, if you raise that number to the power of Q minus 1, then you should get 1. So that is one of our tests, that if that is the case, so we should satisfy the test. So we say that for G, for G, we would follow this one. Select some random H from ZP star. So this is our set that we are working on. So we randomly select some elements from this set, from ZP, and we hope that it passed the test and it turns out to be a generator in the subgroup group. So at random, until that H satisfies this equation. H to the power P minus 1 divided by Q should not equal to 1. Okay, so this is our test. Because if this H is, remember, if this H is a subgroup of this group ZP, then you raise it to the power P minus 1, it would become 1. But we are hoping that, you know, this H is a subgroup of subgroup of this group GQ. So talking about this group GQ, we know that the order of this group GQ is going to be Q, and then that means that if you get some G to the power Q, that should become 1 Q, right? So we need to make sure that the H that we find is not a subgroup, is not the generator of the group P. And if you go back to the chapter 3, I guess, we have tons of details that why we do this test, and this is the same algorithm that we had there. Just now that you know, we just want to check the equality for one of these groups. All right, so it turns out that this is the way that we want to find our generator. And once we have that, so we basically have a generator that we can work on group ZQ. So once we have these things, so we want to randomly choose the X from ZQ star and compute Y equals to the GX mod P. And then we can set our public key to be P, Q, G, and Y. So you see that comparing to El-Gamal, we have some extra Q over here. And our secret key is also going to be P, Q, G, and X. Okay, so slightly different, at least for the key generation and the way that the group that we are working on, first of all, and also the way that we generate the representation of the public key, that we now have that extra Q in both secret key and a public key. So let's see the signature scheme. Let's see how that is different. So it looked like that we send the same signature scheme. So we said that sign on secret key M, and then we return the same things, R and S. But when you see, they would start to become slightly different. So we choose a key, we choose a K randomly from ZQ, and then we compute G to the K mod P and then mod Q. So we do it, you know, back to back. So we first compute this one mod Q, and then we computed this value mod Q, because we want to make sure that our R or values are a member of ZQ. That's how we compute R. So a tiny bit difference, maybe just this mod Q comparing to what we had in El-Gamal. But for S, we would start to see a bit more difference, that we indeed would use the hash function. So maybe the hash function should also be a part of this description to be very concrete, and a hash. The hash function should be concrete. So the way that the S is computed is we find the inverse of K again, mod Q, and then we plug in the hash function, we compute the hash of M plus Rx. Remember, In the previous algorithm, it was like minus Rx, right? So now we have the hash of M and then plus Rx. So those are the two main changes that we see comparing to gamma, and then the verification also looks whole different. So let's go through the verification and check again for yourself to make sure that that holds true. So I would give this one number 2. Let's go down and discuss about this verification. So on the verification side, it says that we need to make sure that R, which we have computed over here, equals to G to the power hash of M, and then Y to the power R, and then the whole thing to the power the inverse of S, mod Q, mod P, mod Q. Okay, let's go do this computation. So what it says is that if we start with G to the power H of hash of M, and then Y to the power R, and then if we raise this one to the inverse of S minus 1, we should get to R. Let's see if we get to. So it turns out that over here inside the parentheses, if I plug in Y is G to the X, so I get G to the RX, G to the hash of M plus Rx, right? So this is Y. Y is G to the X to the power R. We will become Rx, and then we have the same base, so we add them together. And then S is set to be inverse of K hash of M plus Rx. So it is going to be, I'm sorry, let me check it one more time. Yeah, inverse of K, and then we inverse that again. So inverse of K is K itself, and then hash of M plus Rx, and then this one inverse, right? So remember that over here we are computing the inverse of S, which means that if we go to S, we would inverse everything. So this is K inverse. Inverse of inverse is the K itself, and then inverse of this term we just don't know. We just put it inverse of that term. So if you continue with the computation, what we get is G to the hash of M plus Rx, and then you add this one, so we start to multiply them to each other. So we get K times hash of M plus Rx minus 1, the inverse. So it looked like these two big terms would cancel out each other. So all we left with is G to the K. And by definition, G to the K is R mod P mod Q. Becomes R, the whole computation on mod P mod Q, right? So that's it. We have successfully computed our signature, and also the verification makes sense and works. So if I receive a correct signature for the corresponding message, the verification algorithm should help me to do this computation. But one of the things that could draw your attention is that why would this become a standard for signature scheme? And if I go back to the LGML encryption, and you might wander around and like, why wouldn't we use LGML? It look like that if we use hash function, it should also be existential unforgeable. So why not we are using LGML? The answer to that is going to be on some tricky parts. So let me go to the end. Because we choose our Q to be 160 bit prime, and then you see this computation over here, or R and or S is going to be 160 bits. So this value is 160 bits. This S is also 160 bits, right? Because we are computing them mod Q, and Q is 160 bit prime. So if I go back to check the same numbers for L11 encryption, we don't do that. We do those computation mod P or mod P minus 1, almost the same group. And then we said that the P that we choose for ZP could be quite large, maybe a few hundred bits. So it turns out that DSA has a little bit of more efficiency in terms of the size of the signature. So because every time you get you get to sign something, the total signature size, the length of the the signature of SK on message M is going to be 320 bits, right? By only transferring 320 bits, you can compute and transfer the signature. Whereas if you go to the Al-Gamal scheme, that number could be, and not could be, is a lot larger than 320 bits. And that is one of the reasons that people would prefer DSA over Al-Gamal, just because working in a subgroup gave us this benefit to do the signature and with sending and receiving a lot less number of bits. This becomes very important if you imagine how many times on the internet every person would sign things. Every time you try to log into some website or make a secure connection, a lot of time you want to use signature. So if you imagine how many times a day you connect to some website, now most of the website that you connect to is a HTTPS. And every time that you connect to that HTTPS thing, it is very likely that at some point you do sign something. So it would become like some non-negligible portion of the communication on today's internet is all about digital signature. So having shorter number of bits, even though it is a little bit, that would save a lot of bandwidth on the telecom all over the world. So gaining something with the same security, with even a little bit of more efficiency on the number of the bits that you need to transfer, that would be a huge number when you multiply that to the number of the internet users and the number of the connections that they make per day. So I hope that not just that I know that you're passionate about crypto, how different things works. You also have this efficiency hat, and you judge that which algorithm would make sense to utilize in practice, and which one wouldn't really make sense in terms of security. And then when two algorithms they achieve more or less the same level of security, then the next thing that you want to compare is their computation. So it look like that we are more or less doing similar computation, just one that when you're doing computation on the mod Q, so this exponentiations and multiplications would be faster than mod P, because Q is only 160 bits, and we know that our modular exponentiation algorithm it depends on the number of the bits, and therefore that would also bring some computational relief using the DSA, because we are working on a smaller groups with the same security. So therefore whenever we do this exponentiations, multiplications, we are doing a lot less computation. So now that we have two algorithms with a more or less same level of security, we see that DSA has two benefits. One is it is faster because we are working on a subgroup of a large prime P, and then therefore we get some benefits on computation. Those for loops and tedious computation that we have to do is a lot less. Two, the length of the signature that we produce is a lot smaller, and that also helps for communication. So most of the time, speaking of crypto, we have these two goals, right? We want to have more efficiency in terms of computation and also communication. So it looked like that DSA is the algorithm that satisfies both comparing to the Elgamal. And guess what? That is why the DSA is a standardized digital signature on the internet. If you open most of the certificates today, you wouldn't be surprised to see that they are using DSA algorithm for the digital signatures. Right. So I think this is about it. Any questions? We are done with this chapter, so we are going to move away and start to talk about quite brand new things. All right. Look like that is all good. So we start to talk about the new chapter, that is our cryptographic protocols. This is the last chapter that we want to discuss in this semester. Oh, let me check the time. Well, we don't have much time left. I think we won't have time to even finish this page. How about we take a break now and then a little longer, and then you guys come back fresh, because we are going to talk about a very brand new topic. So it would make sense to get yourself some coffee and come back. So let's have a break now, and then we will come back to continue the class.